So let's begin defining our open sets U of p for all p in this countable subset of this closed interval from 0 to 1. So it's all the rationals in between 0 to 1. And we want the property that p less than q implies that u of p is contained, or the closure of u of p is contained in u of q. So the plan is to do this recursively or inductively. So our plan is first to define either the first open set or the first several, and we're going to choose to define the first two, and they're going to be for the boundary points 0 and 1. So we'll take u of 1 to be our entire space minus our closed set B. And let's recall that the plan here is to create a function separating these two closed sets here in this larger space X. So u of 1 is B's complement, which is an open set, by the way, since B is closed. And so it's everything other than B. And we can immediately notice that A is contained in u of 1. And A is closed, so we can use our definition up here to construct a u of 0 containing A, where the closure of u of 0 is contained in u of 1. So that could look something like this. So now let's let this set, we're going to call P of n, denote the first n rationals in our sequence, for which we've defined their open sets, and for any pair, this star property holds, where if we take a pair in this sequence, and we have that P is less than Q, that implies that the closure of the open set corresponding to P is contained within the open set of Q. And this is the inductive step, so now we need a way to go to P of n plus 1, and that will suffice for our definition to define all of these u of p's for all of the rationals within 0 and 1. And afterwards we can actually look at what the sequence might look like, but for now it's not important. We just need to know how to go from the set containing the first n elements of our sequence to the set containing the first n plus 1 elements of our sequence. So we know that for P of n we have the star property, and we're going to get, after the first n elements of our sequence, we're going to get some next element r, and we're going to use a theorem now that's we're not going to prove it, we're just going to state it. It's not so hard to see. So this theorem, what it says is that if you have a finite simply ordered set, and simply ordered means you can compare any two elements within that set, and in this case we have the standard order relation on these rational numbers. And if you have, the theorem says if you have a finite simply ordered set, then every element of that set, except for the minimum and the maximum, has an immediate successor and predecessor. And that's pretty straightforward. I mean, you can just compare all of them and find the one that's closest to your element on either side. So now if we take P of n plus 1 to be P of n union with this new element, or this next element in the sequence, we know that R is going to have an immediate predecessor and immediate successor, because it's not the maximum and it's not the minimum. The minimum is 0, and we already defined it, and the maximum is 1, for which we've already defined open sets. And now what we're going to do is we're going to say, because it has an immediate predecessor and successor, we're going to call them P and S. We're going to first notice that u of P is contained in u of S. So now we can use our definition of normality to find an open set u of R, which contains this closed set u of P, or the closure of u of P, and also where the closure of u of R is contained in u of S. And now, after we've done this, we want to make the assertion that now the star property holds for any pair in this larger set, P of n plus 1. So there's two cases. Case one is for the pair Q1 and Q2, they both belong to P of n. And in that case, by the induction hypothesis, the star property holds. Now, the second case is that we have, as one of the elements of the pair, is R. It's this new element that we're working with, the one that we just added. So if one of these, the elements in this pair is R, then we know we have two cases. We could have that Q2 is less than R, our new element, or Q2 is greater than R. And I'm just going to assume this case for now because this other case follows immediately after we show how we can prove that we still have the star property with Q2 and R. So assume Q2 is less than R, right, without loss of generality, and then we can say that Q2 is less than or equal to P, where P was R's immediate predecessor. Since it's its immediate predecessor, we can't go in between P and R, so it has to be less than or equal to P. So if Q2 is equal to P, then we already know that we defined U of P such that its closure is containing U of R, and we're done, because U of P is just equal to U of Q2. Now if Q2 is less than R, or less than P, then we know that Q2 and P both belong to P of n. Neither of these are the new element, which is R. So in this case, we know that the closure of the open set corresponding to Q2 is contained in the open set corresponding to P, and we already defined the closure of U of P, or we defined this open set such that its closure is contained in U of R, and this just immediately gives us the fact that the closure of UQ2 is contained in U of R. And of course, if we were to have assumed that Q2 is greater than R, it's the exact same proof. So for Pn plus 1, we have the star property. So that we know that when we define this set inductively for every element in the sequence, the resulting set is going to have the case that for any pair of rationals in that interval, Q and P, we have that Q less than P implies the closure of the open set corresponding to Q is contained in the open set corresponding to P. And I know I've said this a couple times, and I just want to be clear on what this property is. This is the star property. Because we're going to now define f of x in terms of these open sets and in terms of which sets actually contain x. But just to be a little more clear, let's actually look at what our sequence might look like. So we know we started out defining our open sets for 1 and 0, where 1 was just everything other than our closed set B. It was B's complement. And 0 was just the open set corresponding to 0 was some open set containing A where its closure was contained in U of 1. So these were the first two elements of our sequence. And now we can imagine iterating through all of the rationals in between 0 and 1 from the following method. We could add 1 to the denominator and then increment the numerator until we get to 1. So we have 1 over 2 as the first addition to the sequence. And then we can't go any further because 2 over 2 just becomes 1. So then we can put another 1 in the denominator. So we have 1 over 3. And now we can go up to 2/3. And of course we can't go further, so now we go to 1/4. And 2/4 we already have, so we skip to 3/4. And of course if we just continue this process, we'll cover every single rational in the interval from 0 to 1. And this is just to give us an idea of what our set of rationals might actually look like when we put it in bijection with the integers, so we make a sequence out of it. And so we started out just by saying U1 is B's complement, and then U0 is just any open set contained in U1 where this contains A, the other closed set that we're separating. And so then when we get 1/2, and this is like what we were going over earlier with taking in a new element r and trying to increase the size of our set. Now r is directly in between 0 and 1. So 0 and 1 are its immediate predecessor and successor in our current set. So then we want to define u of 1/2 such that its closure is contained in u of 1, and such that the closure of u0 is contained in u of 1/2. And then when 1/3 comes in, it's in between 0 and 1/2, and we just continue this process. So this is how we define our collection of open sets here. And now, finally, we can move on to the final step where we actually build our continuous function that's going to separate our closed sets for us. So firstly, let's define this set here, q of x. Actually, no. Before I do this, let's define u of p for all p. So for all p in the rationals. So more than just the interval in between 0 and 1. And the way we do this is we just say for p less than 0, because we defined for all the p in the interval from 0 to 1. So now we need to get everything to the left of this interval and everything to the right. So for p less than 0, we're just going to say up is equal to the empty set. And for p greater than 1, up is just equal to the whole space. And we can verify now that the set of all of these ups has this star property. So now we have an open set for every single rational, and if you take any pair of those rationals, we have that property that we want. Okay, so now we're going to define this set. I'll call it q of x, and we're gonna call, so x will be an element of our topological space that we're working with, and q of x is going to be equal to all the rationals such that the corresponding u of p contains x. And I drew this flip because I accidentally put the open set first, so really this is what I meant.